Hello, good evening, everyone. I'm Kailash Prasad, a PhD scholar from Nano DC Lab, IIT Gandhinagar, and this is the live session 7 for the course Digital Circuit taught by Professor Santanu Chattopadhyay. And we have this session every Tuesday from 6 p.m. to 7 p.m. Right, and our goal is to solve a couple of problems which are based on the topics which we have discussed over the class in the lectures. So let us see uh, what we have done as of now. So this is the course layout, and as of now, what we have done is we have discussed. We started with the number system, then we have discussed about the Boolean algebra, combinational logic, logic gates, all the arithmetic circuit, multiplexer, demultiplexer. Then we have also discussed sequential circuit, and we have discussed finite state machines in our last lecture. And in today's lecture, actually, I have told you guys that okay, I will be discussing the finite state machine in a greater detail today, and we'll see how to make FSM in the today's lecture. And what we will be doing is we will be discussing some of the questions on data converters like ADC and DSC. Okay. So we will start. So I have four example of the same sequence detector. So 1001. So two example for Moore machine and two example for Milli machine. And what we want is we want to design a non-overlapping Moore sequence detector, then overlapping Moore sequence detector, then non-overlapping Milli sequence detector, then overlapping Milli sequence detector. So these are the goal which we currently have. And can anybody tell me how, or everybody knows how an FSM works? Can anybody confirm? Hello? Anyone?
No, sir.
You don't know? Okay. Anyone who knows the difference between Moore machine and the Milli machine?
The Moore machine only based on the present state, and
Hmm.
the Mealy machine based on the state as well as the input.
Okay. Okay.
Obviously, it is a asynchronous one, Mealy. Yeah.
Okay. 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 And any comment on the number of states that will be required for Mealy machine and Moore machine? If I want to detect a n-bit sequence, how many states will be required for a Mealy machine and a Moore machine?
N states, obviously.
Sorry, n states for both. Okay. So let us start today's discussion. Okay. So the anyone else? Anybody want to say something? Okay. So for Moore machine, the output depends on present state. Okay, present state. And for Mealy machine, the output depends on both uh, input and present state. Okay. So this is one of the differences which we have. But why do we require a finite state machine? That is my question first. Anyone wants to answer? Why a finite state machine? No one will be answering. So a finite state machines will be required to design a system, right? So in whenever you design a system or whenever you design a complex logic, there are sequence of event that has been happening, right? And that is the reason why we use FSMs, both Mealy and Moore, to design. So in today's demo, we'll be discussing one of the system that is called a sequence detector. Okay. So the question here, what I have said that okay, I have to design a sequence detector that will detect a sequence 100. it should be a Moore state machine, right? And it should be non-overlapping sequence. Okay, so I have so many constraint over here, right? So let me first tell you what is a overlapping and non-overlapping sequence. So suppose I have a sequence which I have provided like this. Okay, so 1 0 0 1 1 0 0 1 1 0 1. So how many non-overlapping sequences are there for 1 0 0 1? Anybody wants to tell me? So this is my sequence, and how many non-overlapping sequences are there in this what I've written?
Two.
Two. Okay, so this is the 1 0 0 1. Okay, and then this is the 1 0 0 1. Okay, but if I ask how many overlapping sequences are there?
Three.
Right? So how many? So overlapping means that this is one, right? Again, you see this one is overlapped with this, but again, this is a 1 0 0 1, right? And if you see over here, this is 1 0 0 1. So three overlapping sequence. So now you understand. Okay, overlapping means if the number, whatever bit, whatever pattern you want to detect, if it is overlapping with the previous pattern, then it's called overlapping. Otherwise, it's non-overlapping, right? Here, what we want to do in the first part, we want to detect a sequence which is non-overlapping. Okay, so we do not have to worry about whether our sequence is overlapping or our sequence is overlapping or not. Okay, so here the sequence is non-overlapping. So let me design a Moore machine. So see, for Moore machine, if number of states are four, so number of variables are four, we require five variables. Okay, so let me define that. So how to design? So this will be S0, then S1, S2, S3, and S4. Okay, these are five variables, and I have to define the output in the state itself. Why? Because I have told that for Moore machine, the output will only depend on the present state, right? So if you know the state, you know the output. Okay, so only the final state will give me the output one. It means the sequence is detected. Otherwise, the sequence is not detected. Okay, so for this, the output will be one. For this, output will be zero, and this output will be zero. For this, output will be zero, and this also I have to define. Okay, so I've defined five states with its output. Okay, now what I have to do, I have to design the 1 0 0 1 detector. Okay, so suppose if I am in the initial state, okay, and the first thing, uh, so how we will do it, we will check for two conditions, right? Either the input is 0 or the input is 1. Okay, so if my input is 0, can anybody tell me which state I will go? I am here. Okay, I am here. I will start with here. And if my next input is 0, where I will go?
S1.
S1. Okay, anybody else?
It stays in zero.
Yeah, it stays in 0. Okay, because the pattern for moving to S1, right, is actually you have to detect 1, right? So that is the reason. Let me help you, right? This state,
0 0 is not count here.
sorry,
0 0 यहाँ पर नहीं होगा सर.
0 0 नहीं, 0 0 नहीं होगा मतलब क्या पूछ रहे हो?
सर 0 1 जो आप कोड बोले सर वो मैं S1 की तरफ मूव किया.
नहीं
ये
नहीं
S0
नहीं,
जो
जीरो, मैं
0
मैं बस
0.
जीरो के बारे में आपसे पूछ रहा था, ओनली जीरो। अगर बस जीरो आता है
ओके
तो क्या होगा? ओके,
ओके ओके.
right? So see, this is the my initial state. Okay, and so this is my initial state. This state represented one has been detected. This state represented 1 0 has been detected. This state represented 1 0 0 has been detected, and the final state will decide that 1 0 0 1 has been detected. Okay, so if I get a 0 over here, right? Because my pattern is not there, so I will remain here, okay, for 0. So I have two options, right? Either I get 0 or 1. So if I get 1, I will go over here. It means when I go over here, it means 1 has been detected, okay? So again, what I have to do, I have to ask the same question at the next state, whether 0 or 1. right? So if I get a 0 over here, if I get a 0 over here, right, it means what? I have already a 1, right, and I get a 0. It means the sequence has become 1 0, right, which is required over here. So I will go to the next state. Okay. So if 0 comes, I will go to the next state. What if 1 comes? Okay. So already I had a 1, right, and I got a 1. It means the sequence has broken, right? The sequence has broken, and whenever the sequence breaks, what we have to do? Anybody want to tell? Anybody?
It should go to S1.
It will remain at S1, right? It will remain at S1. Okay. Why? Because 1 has been detected, right? So if I am over here, it means 1 is there, right? Because the sequence has been broken. So I will just take care that, okay, this is my first point, right? And then I will try that, okay, what will happen next, right? So let me repeat again for you. In the S0, if I get a 0, I will stay at S0. I will get 1, I will go to next state. If I am at S1, if I get a 0, it means the my next sequence is 1 0. So that is what I want to detect. But if I get 1, it means the sequence has been broken. But if I start over again, right, 1 is this state, right? It means what? I have a 1, so I can stay at this state. I should not go to S0, right? Because I already have a 1. That 1 can be used to detect next sequence. Okay. Now, the next question is, what will happen when we are at S2? Again, I have two questions. If I get a 0, so I will go to next state because I have detected 1 0 0. If I detect 1, right, what will happen? 1 0 1, right? If I detect 1, it means what? Anyone?
It
Excuse me,
goes to
sir.
Yeah.
Sir, how you are, how you wrote this 101001? How sequence getting changed?
Which one you want to question?
Yes, same. You wrote here, no, 1101, 001001.
Okay, how I have written this one?
Yeah, yeah.
Okay,
And
no, no, no. What
you
I
are
have
explaining, no, how to, you are explaining for different sequences, no?
No,
How
no,
you are,
I am just asking for 1001. Okay. So what I want to do, I want to design a state machine which will detect 1001. Okay. So that is my goal. Now I want to design a state machine which will detect 1001. Right. So what I have done is I have defined 5 states because it's a Moore machine. Right. And what I want to detect, I want to detect 1001. So it means, see, the input will come sequentially. So one by one the input will come. Okay. If I get a 1, it means I am at this state. If I get 1 0, I am going to this state. If I get 1 0 0, I am going to this state. And if I am getting 1 0 0 1, I am going to this state. So that's my uh, representation of this number. Okay. So this state actually represented, okay, I have detected this up to this sequence. That is my point. Okay. Is that fine? Is it fine? Hello. Okay, then I should continue. Okay. So if I get a 1, right, I have two options, right? Uh, okay, okay. Thank you, Kamal. So if I get a 1, right? So I got 101. My sequence has broken, right? So if my sequence has broken, what I can do? I can go to a state where I have detected 1, right? I can go to this state. Okay. So this state means I have currently only have 1, right? So, okay, sorry. I think I've drawn it wrong. 1 minute. Yeah. So from here, right? If I get 0, I will go there. But if I get 1, I will go to this state, right? So that's how it is. Again, if at S3, if I get a 0, it means my sequence is 100, right? 100 means my sequence has broken, right? So this is my current variable and my sequence cannot start with 0, right? So in this case, what I will do is if I get a 0, I have to go to the initial state. If I get a 1, I will go over here. If I get a 1, I will go to the next state, right? It means what happened? 1001. It means my uh, yeah, 1001. What does it mean? That I have detected the sequence, right? And I am at state 4. After that, I again have two options, right? If I can get 1 or 0, right? So 1001, right? If I get a 0, if I get a 0, right? Because it is a non-overlapping case, because it is a non, what you will do? You will directly go to S0, right? Because now its sequence has directly broken. And if I am getting 1, it means what I am getting 10011. Where I will go? I will go to S1. Okay, so this is my 1. Is this clear with everybody? How I have drawn this Moore FSM? Everybody, it is clear how I have drawn Moore FSM? Hello.
Sir, I have confusion.
Okay, yeah. What is the question? Should I repeat?
Question, no, yeah, yeah.
Okay. So let me repeat for you. So you should listen it carefully. Why? Because this is an extremely important concept, right? Already been taught in the class, right? But because in the last session you guys have asked, so that is the reason I'm teaching you guys over here. Okay. So what I want to detect is 1001. That is my goal. Okay. I want to detect a 4 bit sequence. Okay. So whenever I get a 4-bit sequence, my output should be 1, right? So my sequence is X. Okay. And I want to get Y output, right? Y output is 1, right? For detecting 4-bit sequence for a Moore machine, I require 5 state. Okay. So I write S0, sorry. Yeah. S0, then S1, S2, S3, and S4. Okay. And what does the output of each of the state represent? Because this is a Moore machine, every state will have some output corresponding to it. So for this case, y is equal to 0. For this case also, y is equal to 0. Y is equal to 0. Here also y equal to 0. And here also y equal to 0. Here y equal to 1. If you get to S4, it means y is 1. Okay. So I will make these 4 states. Very simple. Okay. Now what I will do, I will define the definition of each state, right? And this is for only our purpose. Okay, this has nothing to do with the state machine. This is my initial state. I will start over from here. Okay, so no pattern has been coming, or I do not have anything now. As soon as I get a pattern, if I get 1, I will go to next state. Then if I get a 0 after that, after 1, if I get a 0, it means what I got? 1 0, right? I will go to next state. After that, if I
Sir,
get, yes,
sir, why we not start one from initial state? Why we start zero from?
1 from initial state.
Yes, sir.
You
This
require an initial
the
state, right?
sequence is 10014 bit. So
Yes.
why we taking as zero as starting from zero?
No, no, I'm not taking S0 as a 0. I'm taking S0 as an initial state. You have to start from somewhere, right? S0 is you do not
So,
have a input as of
what
now,
I'm asking is,
right? S0 means you do not have
okay,
an input now. As soon as you get an input, you have two options. Either you get one input or zero input, right? So
Yes. Yes, sir.
my initial condition will be if I don't have a 1, that will be my initial condition. If I have 1, I have to go to the next step. That's my point, right? So suppose if you get a
Okay, sir.
sequence and suddenly a zero comes, right, and your sequence break, right, where will you go? You don't have any state to go to an initial position, right? So that is the reason why you require an initial state. Okay.
So, so we require initial, but why we not starting initial one from initial state, sir?
One is our sequence, right? If I have one over initial state, just give me an example. I have detected 1 0 0 1, then and after I got a zero. Which state? Sorry, it is this is the sequence, right? I got over here, right? And after that, get a zero, right? My question is, where should I go? कहाँ से कहाँ पे draw करोगे अपने diagram को? That's my question. Can you answer that? I have detected this sequence
No,
and I went to IS4, right? And I have a zero over here. Is there any state which
no,
defines, if this state defines one,
okay,
right, where should I go? Should I go over here? No, right? I cannot go over there, any place.
and the sequence break
Ah,
after one.
yes, then the sequence breaks. So there should be an initial state. Okay?
Okay, sir.
Yeah.
Okay, okay.
Right? And this initial state will be one if your sequence, sorry, it will be zero if your sequence is starting from one. It will be one if your sequence is starting from zero, right? Suppose if I've written that my sequence is this, in that case, the first initial state will represent the complementary of that. It's just a representation, okay? So I will not explicitly write out that, but it's just a representation. Okay? Got my point?
Yes, sir. Please proceed.
So now this state will represent 100 and this state will represent 1001, right? I will go quickly over this. Now, what we want to do is we want to design a state machine. I want to detect 1001, right? Very simple. I have two options. If I get a 1, right, I will go to next state because this is my 1, right? And if I get a 0, I will stay over here, okay? Because there is no sequence as such, right? Again, if I get a 0 over here, I will go to next state. Why? Because 10 has been detected and this state represent 10. But if I get a 1, right? If I get a 1, it means I am here only, right? After 1, if I get a 1, it means this 1 is of no use because this is not part of my sequence. But this will stay over here, right? Again, I have two options. If I get a 0, I will go to next state because this represent 100, okay? And after that, if I get a 1, so I will go over here, right? Because it will be 10 and after that it is 1, right? So I will discard because the sequence is break. If this 1 is useful, yes, 1 is useful, I will go to one state, right? If yeah, so after that, uh, I have again right? I have again one option. If I get a 0, it means 1000, right? So the sequence breaks. So sequence is of no use. And do we have a state which represent or this 0 is of any use? No. So we have to go to initial state. So we will go to initial state, right? If I get a 1 over here, right, I will go to next state. It means my sequence has been completed and the output is 1, right? Again, after that, I can get either 0 or 1. If I get a 0, right, it means 1 0 0 1 then 0, right? 0 means sequence has broken, right? Because I need 1. So you will go to this state, initial state for 0. But if I get a 1, right, 1 0 0 1 1, so up to this part is of no use for me because this has already been gone. This 1 can be used for next sequence. So what I will do, I will go to this 1 state. Okay, so this is how a 1001 Moore over non-overlapping detector looks like. Is that clear, everybody? Okay, so I will quickly go to the other one. Here we have milli machine. Okay, earlier it was Moore, now we have milli, and milli is simpler than Moore. Okay, so in milli machine, the number of states that is required is same as the number of input variable. What I want to detect is 1001. If you don't understand, please let me know. I will quickly go, right? S0. So I have four state, S1, S2, and S3. And please note that in Mealy machine, the output not only depends on state, it also depends on input, right? So I cannot define output in my state, just like what I have done over here. I cannot do that. Okay. So in this case, what I will do is I will design my 1001 detector in a similar manner how I have defined earlier, right? So I am at my initial state, right? If I get a 1, right? If I get a 1, I will go to here, right? So this is my 1. Has my output or the sequence has been completed? The answer is no, because I have only detected 1 up to here. So I will give my output 0. So please note that this is my input, this is my output. Okay. If I get an input 1, I will go to next state. The state has changed, but the output remains 0, right? If I get a 0, so the state will also not change, just like the previous case, and output remains 0, right? Now in the S1, I have again two options. If my output, sorry, input is 0, so it means I will go to the next state and the output remains 0 because the sequence has not completed, right? So what does it mean? The S2 represent what, right? I have detected 1, then I have detected 0, right? So S2 represent that, right? But if I get a 1 in the S2, I have to go to this state because this state represent 1, okay? So 1, then the output is 0, okay? Again, if I get 0, I will go to the next state. I will go to the next state. The output will remain 0, right? But if I get say 1, right? So the sequence will be 101. So the sequence has broken. I have to go to one state, right? I will go to one state. Okay, sorry. Okay, I think I have yeah, I have messed up. Okay, sorry for that. So
I think you are doing correct. Please go.
but I think I have missed this one, right? So if I remains at 1, I will go to,
Yeah, that you missed.
and this is for this state. Okay. Yeah. So now in this case, if I get 0, I will go here. But if I get 1, I will go to S1 because S1 shows that I have only detected 1. This state shows I have detected 10. This state shows I have detected up to 100. Now I am in this state, right? I have two options. Either I can get a 0 or a 1, right? If I get a 0, 1 0, then 0 and a 0, right? It means the sequence has broken. I have to go to initial state. So I will go to this particular place, right? So this is my 0 and the output is 0, right? But if I get a 1, 1 0 0 1, what does it mean? That the sequence has been completed. At the same time, I can go to a state which shows that okay, a sequence has been completed, so the output will be 1. But again, the sequence has been broken, so I have to just move it and I have to go to a state which represent 1, right? So no, no, no. Okay, so if I do that, so that will be an overlapping sequence. But in this case, what we will do, in any case, I have to come to an initial state because what I have done is I have detected 1, right? And I will go to my initial state. So how the Mealy FSM work is it takes one state lesser. Why? Because my output depends on both input and the state, right? So it the output can change as soon as my input is changing, right? So anybody wants to tell what can be the advantage of and disadvantage of the Mealy approach? So Mealy takes four states. What could be the advantage and what could be the disadvantage of Mealy approach?
The advantage is means we have lesser number of states, so we may go for the less number of flip flops.
Lesser number of flip flops. So what does it will translate to?
Obviously, reduction.
In terms of power area or
Obviously, in time of cost and complexity.
yeah, the cost and the complexity will go down, and it will be much faster, right, as compared to the move.
Yeah, right.
But what will be the disadvantage? See, one of the
Maybe the input causes something, right? It may be if input changes, the output may be.
Yeah, so that is exactly correct. If the input is changing, the output changes, right? And so what does it do? It make your machine, the state machine which you have designed, a bit asynchronous, right? And you don't want that anything to change when my clock is not or the positive edge of the clock is not there, right? So you don't want that kind of machine, so it's your choice. You want a faster machine, but it will come with an overhead that it will make your circuit asynchronous, and with asynchronous circuit there are various problems like glitches and that can happen. While in Moore machine, the output will only change at the clock edge when the state changes, right? However, it will be a bit slower as compared to milli machine, right? Is that clear?
Yes, sir.
So I have one more example where what I've done is I have written the sequence detector, but for overlapping sequences, right? So overlapping means that if I get 1001 and after that also I get 1001, right? What I will do is I will overlap it. So I want to detect both, right? I want to detect both. Okay. So what? Uh, So how to approach this? It is very simple, right? In the same manner how we will do that. So first we will design my states as 0, as 1, as 2, as 3, and as 4. Okay, the output remains 0, then 0, then 0, then 0. In this state, the output will be 1. Okay, so I will make all the states, and please, so it's the basic, very easy way of doing. So this is my initial state. This is my 1, then this is my 0, then sorry 1 0, this is my 1 0 0, and this is my 1 0 0 1. Okay, so if I get a 0, I will stay here. Okay, I will change my color. Yeah, and if I get a 1, I will go to next state, right? Now if I get a 0 after this, right, I will go to next state. If I get a 1, I will stay over here, right, because 1 is there. After that, if I get a 0, I will go to next state. Okay. If I get a 1, I will again be here, right, in the previous state. This is exactly same how we were doing earlier. Okay. After that, if I get a 0, it means 1 0 0 0, right? So the sequence has broken, right? So what I will do, I will go to this state, initial state, right? But if I get a 1, right, I will go to the next state, 1 0 0 1, right? Now I have two options. Okay, so after that 1 0 0 1, right, if I get a 0, right, so you see that although the sequence has broken, but if you take the previous state, you see it will represent 1 0. Okay, it will represent 1 0, and it can also represent 0 1 0, but we do not have any 0 1 0 state, but we have 1 0 state. So what we have to do, we have to go to this state. Okay, so as soon as you get 0, you will go to this state, right? So that is the change in the overlapping sequences, right? You are detecting the overlapping pattern. Okay, so you get 0 over here, but if I get 1 0 0 1 1, right? So let us check, do we have 0 0 1 1? No. Do we have 0 1 1? No. Do we have 1 1? No. Do we have 1 only? Yes, we have 1. So we have to go to this state. Is this clear, everybody? How I have designed the overlapping one and what is the difference? So see, the difference is for one it would have been in the same place, but for 0, right, it would have been gone to the initial state, right? But in our case, because we are detecting overlapping, our pattern is still intact, right? So for 2 bits are intact. So I will wait for the next bit, okay, and I will go to this state which represent 1 0. Is that clear? Everybody, is that clear? Okay, cool. Moving to the final one, okay, sequence detector 1001. This is milli overlapping. Okay, the previous one was more overlapping, now going to milli overlapping. Okay, so see, we have seen the same sequence but for 4 different combination of state machine, and I will quickly go through it: S1, S2, S3, and S4. Okay, so this represent 1, this is 1 0, this is 1 0 0. Okay, this is my initial state. Now if I get a 0, I will stay over here. If I get a 1, right, and I have to also show the output, right, 0 by 0, 1, the output still remains 0. Again, if I get a 0, I go to next state. Okay, if I get a 1, I will remain over here, the output is still 0. In S3, if I get a 0, I will go to next state. If I get a 1, right, I will go to the previous state. 1, right, the output still remains 0. After that, if you get a 1, right, so what you have done, 1 0 0 you have detected. If you get a 1, right, uh, where you have to go, you have to go to this state, you get to this state, right? So if you get a 1, you will go to this state. Why? Because this detects a 1, right? Your final output will be 1. It means your 1001 is completed and 1 is there, right? Because 0 1 0 0 1, we do not have any state corresponding to that. But if I get a 0 1 0 0 0, the sequence has completely broken. I do not have any overlapping state of 1 triple 0. I will go to the initial state, right? If I get 0, the output remains 0. Only for this case, the output is 1. Right, so this is the milli overlapping case. You see there is a slight difference in the Moore's overlapping case. For uh, if after 1, if I get a 0, I had a state over here, I had a state over here. But for uh, milli overlapping case, right, after so because I do not have an extra state, what it does, it changes your state machine slightly a bit, right? If you so this is a perfect example which exactly shows the difference between the milli and mode state machine, how they behave differently for overlapping and non-overlapping case, right? uh, Everybody, is that clear, the 4 examples which we have done today? You can comment, you can write in the chat box such that I know, okay, other students about other than Madhubala. Okay, right? Please make sure that you understand the concept of the milli and more overlapping machine. And
Sir, sir, I understood that in either milli or more machines, how the state diagram is being drawn.
yes,
Just the input and the in the more machine, I think we indicate the input and the output also.
in the more machine, the output will be denoted by the state itself. So the state
Okay.
represent the
Okay. In the milli machine, we indicate both the input and output.
at the same time. Yes, because the output
In
depends
the
on state also and the input also.
I didn't understand
Okay,
what.
see this output, or see this output 1 is dependent on the state. The first thing is state. Why? Because if this state represent what? This represent that, okay, I got 1 0 0. After that, if I get 1, right, then my output is 1. It means the output depends on state, whether the state is 1 0 0 or not, right? If it would
Yes.
have been any other state, the output would not have been 1, right? Just like in this
But
case.
it is true for both milli and more machines. No? If the sequence is not 1001, both melee and more, both will detect the sequence is not completed, both will detect 0.
Yeah, both will detect 0. But how you draw the diagram and how you are designing the machine, the output, see, the thing is, as soon as you get the input, you will get the output, right? After this particular state. That's how the melee machine looks like. But if you see the Moore machine, there is a dedicated state which says that, okay, if I am in this state, it means my output is 1. However, in the case of melee, I do not have a dedicated state which says that if I am at this state, my output is 1. No,
Okay,
right?
sir. Okay. Okay.
Right?
Yes.
So
Yes.
doesn't matter what input pattern has been provided. If I have and obviously it will matter because you will get to this state only if your input is 1001, but after reaching to this state you will directly make the output 1, right? So it means the state is the important part, right? The path of reaching the state is the input, but the state is defining the output finally. However, in this case, you are at this state, but you are waiting for the input, that as soon as you get the input you will change the output, right?
Okay, sir. Yes.
So, yeah, lot of discussion on FSM, right? I hope that this would have cleared some of your doubts regarding how you design milli and more FSM, right? And you can transition this into tables and all. You write the Verilog code or design digital circuits, but the concept remains the same. The concept will be this only. Okay. Now, our main goal of after this, the next goal is to solve some of the questions on ADCs. Okay, ADCs and DSCs. So the first question is, how many comparators are required for a 4-bit flash type ADC? Anybody knows? Or anybody wants to answer? ADC means what? Anybody? What is
Analog to digital converter.
ADC means analog to digital converter. Okay. Hers, how do I pronounce your name? Harsit, I think, right? Harsit. So analog to digital converter, and he is saying that the answer is 15. What about the other student?
Is it using the encoder?
Using the encoder. How many comparators are required? Yeah,
In that case, that should be 4 power, that is 2 power 4, right?
it won't be 2 to the power 4. It will be what? So the number of ADC, number of
63 maybe.
no, the number of ADC is 2 to the power n minus 1. Sorry, number of comparators for a flash type ADC. Yeah, that's correct. Okay, it is 2 to the power n minus 1, right? So here n is 4, 2 to the power 4 minus 1. This will be 15. So 15 is the answer. 2 to the power 4 is 6. Yeah, 2 to the power 4 is 16, right? Yeah, 2 to the power 4 is 16. So the answer is 15. Okay. And please note why it is like that. I will just give you a brief example and you will understand. Okay, you will understand. Sorry. So I have given you the answer. It is 15 because if you see the architecture of flash type ADC, you will understand. I have, so for a 4-bit ADC, how what kind of encoder I want? Anybody wants to know? Oh, sorry, tell what kind of encoder I want for a 4-bit ADC? 16 is to 4, right? So 16 is to 4 encoder. So I have 16 lines. Okay. Yeah. And what happened? The all the 16 lines are actually connected with an XOR gate. It's like this, right? So the first one is connected to ground, and these two. So I will have another XOR gate. Okay, these two will be actually connected to one comparator. Okay, and similarly it will happen. So if you will have 16 gates, right? For connecting 16 gates, how many comparators you require? 15 comparators you will require, right? Because you're making 15 connection. The first one will be ground, and the last one will be connected to a comparator. So this number of comparators will be 2 to the power n minus 1. So that is the architecture of a flash type ADC, and that is the reason why. So the straight away answer, if you want, it will be 2 to the power n minus 1, but you should understand, okay, how the architecture is. Okay. Moving to the second question, I have an 8-bit DAC, right, with a step size of 25 millivolt. What will be the full scale output voltage? That's my question. What will be the full scale output voltage? If I have a DAC, 8-bit DAC, okay, I have an 8-bit DAC. So how many patterns it can generate, 8-bit DAC? Or anybody? How many analog voltage it will generate? DAC is a digital to analog to converter, okay? Digital to analog converter. So if I have an 8-bit DAC, how many analog voltage will be generated? How many numbers can be represented using 8 bits? Anybody? 2 to the power 8. So that's correct, right? So 2 to the power 8 numbers can be represented, right? So it means 256 numbers can be represented using a digital to analog converter, right? So for representing 256 different numbers, right? So suppose I want to represent, say, 3 numbers, okay? If I have 3 numbers, and I have, say, I want to if I have 3 number or 4 numbers, right? So this is my 00, this is my 01, this is my 10, then 11, okay? And I want, suppose I have the VDD supply of 12 volt, right? So initial value will be 0, this will be 12, right? And this will be how much? I think I have not taken a correct number. So if I take 10, if I take 10, right? So this will be 2.5. See, okay, let me do like this: 0, 4, 8, 12. So 12 is fine. I think I'm fine with 12, right? So if I have 12 numbers, okay, individual step size will be 4 millivolt, okay, and you see, so there will be 3 steps I have to take to reach to 12, okay, 3 steps I have to take. For representing 8-bit number, so this is a 2-bit, I require 3 steps. For representing, because each step size was 4 millivolt, so full scale was 12 millivolt, okay, full scale was 12 millivolt, okay, 12 millivolt. I can directly give you formula, but let me make you understand why this formula works, right? And for representing a 2-bit number, right, each step size is 4 millivolt. So 4 is multiplied by 2 to the power n minus 1, right? 4 millivolt is multiplied by 2 to the power n minus 1. 2 to the power n, then minus 1, right? So the full scale output voltage will be, this is my step size multiplied by 2 to the power n minus 1, right? So here the output will be 25 millivolt into 2 to the power n minus 1 means 256 minus 1, 255. What will be the value? Anybody wants to tell?
6.75.
Yeah, so this will be 6375 millivolt, right? Which will be 6.375 volt. Everybody understand? So you have to remember this part, right? But you should know that how we are getting this formula, because I have just given you an example for 2-bit. You can scale this formula to an n bit. Okay, is that clear, everybody? Everyone, is that clear? Okay.
Yes.
So moving to next question, maximum conversion time of 8-bit successive approximation ADC is for a 2 megahertz clock frequency is, okay, my clock frequency is 2 megahertz. and 8-bit SAR ADC I have over here, right? What is the maximum conversion time? So how much cycle it takes for conversion of a SAR ADC? So I have a SAR ADC, right? If I do an n-bit conversion, okay, how much cycle will it take? Anyone? Have you heard of SAR ADC? Anyone? Okay.
Can you please give a small introduction about the SRDC?
You require any small introduction. Okay, I cannot go into extreme detail of the circuit, right? Because you should watch the lecture. But how does a SAR ADC work? Is you have a sample and hold circuit. Okay, so here I will provide an analog voltage. Okay, I have a sample and hold circuit. So this is called a sample and hold circuit. Okay, and then what I have a comparator. Okay, so there will be one comparator like this. So let me remove this. Okay, and it will be connected to a SAR register. Okay, a successive approximation register, SAR register, and you will get outputs. Okay, whatever number of bits you have. Okay, if you have 8 bits, you will get 8 outputs. Okay, then this is actually fed to a digital to analog converter, DAC. Okay, and then in digital to analog converter I have put a reference voltage so that it will compare with the reference voltage, and you will get an analog voltage, and this is connected to your comparator, right? So how does it work is if you get an 11 volt over here. Okay, if you get an 11 volt here, so the sample and hold circuit, it is nothing but a switch, uh, the switch and a capacitor. It's like that, right? It will hold the value of your 11 volt here. Okay, initially what you do, you initialize with say VDD by 2 or kind of value, right? Or the SAR logic behaves like this, right? So initially you initialize with 1 0 0 0 0 0, right? And whatever the value you are getting corresponding to that, uh, you will try to provide a digital to analog value over here. So suppose you are getting here, if it is say 16 volts, so you will get 8 volt here, right? And you will compare whether it is greater or lesser. If it is greater, right, so you will get an 1. If it is lesser, you will get a 0. This SAR will work, and this cycle will keep on going, right, in a binary search fashion, such that you will finally get the SAR logic, sorry, the final output. So this is the basic block diagram of a SAR logic. Okay, you have a voltage and you keep on sampling, right, and then you get an output. So how you can think of like that, okay, I have an 11 volt which has to be converted into digital. So first what I will do, and suppose maximum VDD is 16 millivolt, 16 volt. Okay, so first I will do, I will compare with 8 volt. So 11 will be compared with 8 volt. If it is lesser than 8 volt, you will go down. If it is greater than 8 volt, you will go up, right? So if it is greater, right, so you will get an 1 output. Okay, so here in our case it is greater, right? So now 8 is there, upper limit is 16, so I will compare with 12. I will compare with 12. Is 11 greater than 12? No, right? So I will go down. If it would have been greater, you will go up, right? So if you have gone down, so here the output is 1, here the output is 0, like this, right? And then you will keep doing that, you will keep doing that. So if this is 12, now you have 8 and 12, you will compare with 10, right? Is 11 is greater, so you will compare with the between of the two values. Okay, you will compare with 8 and 12, sorry, the mid of 8 and 12. So this is my 10, right? And please note that from where these values are coming, right? So these values are coming from this digital to analog converter, from where you are actually comparing. Okay, you are comparing over here. You see, you are comparing over here, right? And these whole values are being generated by this digital to analog converter. Okay, and you will keep on doing that as soon yeah, you will get the output. Okay, so the SAR logic, did you get some idea about the SAR logic? I'm not sure you have understood it completely, but you might have some idea about SAR logic, right? So this is how the SAR logic is been designed. Okay, now what you have to do is you have to tell me. So again, right, if you don't know about SAR logic, what you should do, you should go and watch the lecture, and you should understand the SAR logic. For our case, the answer actually is, what do you want? Conversion time. So the conversion time is, I think somebody has said, is it is n is the number of bits times what is the time period. Okay, time period. This is the conversion time. So in our case, n is 8. The time period is 1 by 2 megahertz. So this will be 1 by 2 into 10 to the power 6, right? So this will be 8 into 0.5 into 10 to the power minus 6. This will be 4 nanosecond. Sorry, 4 microsecond. Okay, 4 microsecond. So the answer is B. So the conversion time is, because it takes n cycles. Okay, so if you have 8 bits RADC, it will take 8 cycles to get the final output. That's the simple logic. Okay, and it works in this kind of fashion. Why it takes 8 cycle? In the first cycle it will do this, in the second cycle, and in the third cycle it will keep on comparing. Okay, till you get the final output. Everybody is clear?
Yes.
Okay, thank you. So moving to next question, a simple one, not a very simple one, but it's a simple one because I've already given you the formula, right? So this is a circuit, right? And what you have to tell me is what will be the output of the following circuits, right? So this is my VO, right? What will be the output? So I have four options: -4, -5, -6, -8, right? And the input that has been provided is B4. This is 1. Okay. B3. This is 0. B2. This is 1. Right? B1. This is 0. Okay, and the reference voltage Vref, where is the Vref? This is 16 volt. Okay, and you see the current in each branch is being shown. So anybody wants to answer this? -5. Okay, Madhubalan is saying it is -5. Anybody else? Okay, so let me quickly tell you how does it work. Okay, so the output voltage V0 is equal to I into R. Okay, so V is IR, right? So it because it's an inverting amplifier. This is minus I into R, right? And this is the total I, whatever I'm getting over here, total I. Okay, so I require the total I. Okay, and that has to be multiplied by R. Okay, so so this will be how we have to calculate this is for the first branch. I will calculate, right? For the first branch, if you see uh, the voltage over here is or the value over here is V4, right? See, on the current will only flow if my V4 is 1, right? So if I write for this particular case, so B4 multiplied by whatever the reference voltage you have, right, into I, right? I is your 1 by 16, right, into R, right? So this will be the current of the first path, this path, okay, the current of the first path. Similarly, the current of the second part will be B3 into Vref into 1 by 8 R, right, plus B2 into Vref into 1 by 4 R plus B1 into Vref into 1 by 2R, and you multiply everything because this is the current with R, right? So R in the every path will get cancelled. Okay. Now let us simplify it. You see that B1 and B3 is 0. So this part is gone, this part is gone. We are remained with the two part, and R can be cancelled, right? And B4 and B2 is 1. So Vref by 16 plus Vref by 4. Okay, so this is what you are getting. So Vref is 16, so 16 by 16, and please note that this is negative. Okay, this is negative. So 16 by 16 plus 16 by 4. Okay, minus. So this will be 1 plus 4. So minus. This will be minus 5. So the answer is minus 5. So whoever has said minus 5 is the answer, that is correct. So for approaching this logic or this kind of logic, so it's very simple. What you have to do is you have to find current is already given for you, right? So I by 2, I by 4, I by 8, and I by 16, right? So on the basis of that, what you have to do, you have to find out the current, and then you multiply it with the resistance, right? So if you and the current should be in terms of voltage reference and resistor, right, such that the resistor will get cancelled out. Okay, so what I have done over here, I have just done that, right? So I have converted current in terms of voltage reference and resistor. So any question in this part? And I have written the entire formula over here, right? So you can just extend this formula easily. Okay, any questions? Okay, so if you
In case if RF is not equal to R, what will be the equation case?
if RF is not equal to R,
Yeah, it may be in case
so
it is.
no, so it won't be any different, right? So this R will be RF only, as simple as that, right? And R you take the common, so it will be RF by R, so it will be minus RF by R, right? Multiplied by whatever the value you have, right? And the question will provide you the value of RF and R. Okay, otherwise it will
Okay.
not. The question will have to provide if that is the case. Okay.
Yeah. Thank you.
Moving to the last question we have is I think this is last or second last. Okay, second last question. Right, it's a very simple one. Which of the following resistances network can be used as a 3-bit R2R ladder DAC? Okay, so anybody wants to answer that? You just see the difference is the resistance. Here it is 1K, 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 2K, and 2K, 1K, 1K. So that's the resistances we have, right? And I want to behave it like as R2R ladder ADC. Which of the option is correct? 1 and 2, 1 and 3, only 3, only 1. Okay, Madhubalan is saying it is 3. I will just tell you in the R2R ladder ADC, right? Okay, D, Harstik is saying D. So the first one he is saying. In the R2R ladder ADC, you should have the V2, if it is V2, is equal to twice of V1 is equal to 4 of V0, right? So this is the thing you want. Okay. So what I will do is uh, I will go with the this part. Okay, this seems to be a symmetric one for me. Okay, and how will I approach this question? Why I say that it's a symmetric one, right? I will calculate V2. right? And you can apply superposition. Okay, so when you calculate V2, you can make it 0, make it 0. Okay, for calculating the value of V2. Okay, you see how the circuit will look like. These are 2K and this 2K is in parallel, right? So it will be like this. It will be like this. Okay, this will be 1K because these 2K and these 2K are parallel. This will be 1K, and here it is 2K, right? This is also 2K V2, right? And I have connected this to 0, and this is 1K, right? 1K and 1K in series, 2K in parallel. So this 2K and 2K will be again in parallel. So this will make, sorry, yeah, this will make the circuit look like this, 2K. Okay, so here it is 1K, right? Because 2K and 2K are parallel, it is again 1K. Okay, here it is V. This is my V0, right? And sorry, V2, and you can see it is 2K, right? So my V2 is, so the 2K resistance is in parallel with the 2K resistance. So V2 looks like this. V2 looks like 2K and 2K, and this is my V. Okay. So the V2 will be what? Anybody wants to tell me in terms of V? If this is ground, if this is my circuit, anybody wants to tell me what will be the value of V2? See, two resistance which are equal and the voltage is connected. Okay, nobody wants to tell me? Half. Okay, let's see. So I will write a nodal equation, V2 minus V by 2K. Okay, because there is only one path. Okay, V2 minus V by 2K plus, or let me do other way around, V minus V2 by 2K plus V by 2K, okay, is equal to 0. Okay, so V by 2K plus V by 2K is equal to V2 by 2K. So that's how it is. So 2K will cancel from everywhere. V2 equal to twice of V, right? So you will get like that. Now what you have to do is you have to solve for V1 and V2. Okay, and if you see that V equal to V by 2, sorry, V2 by 2, that's how it is when you will get from here. It means what is happening if I current is flowing from here it is going I by 2, and here it is going I by 2. Okay, and because it's a symmetric design, you will understand that this I by 2 will go here as I by 4 and here as an I by 4. Okay, and this I by 4 will go here as an I by 8 and here as an I by 8. Okay, and because you have 2K resistance, right, so it will be multiplied by 2, right? So V2 is equal to, sorry, V equal to V2 by 2, right? V equal to V1 by 4, and sorry, and V is equal to V0. I think I have done something here. Okay, okay, I think it is correct, right? So see, I by 2, I by 4, and I by 8, right? So it is the in the ratio of whatever ratio we want, right? 1 is to 2 is to 4, right? And if this 2 will be multiplied, right? So if this 2 will be the 2K, so V is equal to IR, right? Everywhere if you do see the potential drop, normalize, right? So there will be 1V, here it will be 2V, and here will be 4V, like this, right? So if you see this particular diagram, I think I have uh, made it more clumsier. Okay, if you see this particular diagram over here, cleaner in a cleaner manner, right? If this is my I, this will be I by 2, and this will be I by 2. Here it will be I by 4. Here it will be I by 4. Here it will be I by 8, and here it will be I by 8. Right? So it will be in the ratio. If voltage you will calculate, right? So V2, if you will calculate, right? This will be I by 2 into V, right? So I by 2 into 2K, right? V1 will be I by 2 into, sorry, I by 4 into 2K, and V2 is equal to I by 8 into twice K, right? So V2 is equal to I, right? So the K unit I'm not, I'm just ignoring, okay? So you should know that, okay, this is I into R, right? So the unit is a volt, and so this will be V2. V1 is equal to, uh, in this case, I by 2, right? And V2 is equal to I by 4, right? And if you see, the V2 is actually twice of V1, right? Is equal to twice or 4 times of V0. Okay. And why I can easily write I by 2, I by 4, and I by 8. If you see, this 2K and 2K will combine, this 2K and this 2K will combine, will give you 1K, and 1K and 1K in series is 2K. Again, 2K and 2K combined gives you 1K, right? 1K and 1K in series will give you 2K, and it is 2K, right? So it is extremely symmetric design. In all the other case, you see, if you combine 2K and 1K, it will be some number which will not be in power of 2. Again, in this particular case, right, over here, if you combine this 2K and 1K, it will be some number which will not be in power of 2, right? So how to approach this? I have solved this for you, but how to approach this question, you just have to see the symmetricity, right? Whenever you design an R2R ladder, whenever you design an R2R ladder, what will happen? You just have to see the last node, the resistance of last these two nodes will remain same, right? And as soon as you apply superposition theorem, it will make sure that the current is being divided into half, then 1 by 4, then 1 by 8 in all the branches. So is that clear what I have said, or should I repeat again?
Clear.
It's clear. Okay. Okay. Last quick question, because we have done so many questions, it will be extremely simple for you. Please note, for an op amp, right, if this node is ground, this will be what? This will be virtual ground. Okay, virtual ground, it will behave like a 0. So you should know that this is the concept of virtual ground, we say. Okay, virtual ground. Okay, so now what we will do, we will try to solve this quickly. Okay, so you see, here it is 2R, and this is 2R. So the equivalent of 2R and 2R, what it will be? 2R and 2R, it will be R, right? So it will be like this. Anybody wants to answer directly? Right? After every stage I will make. Okay, so this is my ground, this is my ground, and this is my R, and this is my 2R. Here it is V, here it is ground, and here it is 2R, right? Again, you see, this is my 2R, this is my 2R, right? So the 2R and 2R will combine, will make, because these are in parallel. Okay, whenever resistances are in parallel, it will be half, right, if they do the same resistance. So the 2R and 2R will be R plus R, that will be again 2R, right? So the circuit will look like, this V wala, it will be as it is, V, and everything has combined, which has become 2R, right? Here it is 2R, right? And now you have an op-amp minus plus, which is connected to ground, and this node is connected to V0. Okay, this is R, this is I, and please note that this is 0. Okay, and this node is also grounded. Okay, this is also 0. So and this is 2R. What I will do, I will write this as Vx. Okay, and I will try to apply the nodal equation over here. So if I apply this, Vx by twice of R plus Vx minus V of twice of R plus Vx minus 0, right, of twice of R is equal to 0. Okay, so the 2R will go. So there are 3Vx. 3Vx is equal to minus V. This is equal to V, and Vx is equal to V by 3. Right. So this is one equation we got. Okay. The other equation which we can apply from here. Okay. You can see. So if you see the current which is uh, coming from here will be going over here, right? The same current. So Vx by twice of R is equal to minus V0 by R. Okay. How I have written this equation? Vx minus 0 by twice R. Okay. 0 minus V0 by R. Okay. I have equated it. R will be cancelled. So V0 equal to minus Vx by 2. Okay, and Vx is equal to V by 3. So V0 equal to minus of 1 by 2 of V by 3. So this will be minus of V by 6. Okay, so C is the answer.
Can you please explain me this step, that is the Vx by 2R is equal to minus V naught by R? Yeah.
I can explain that. Okay, so what I will do over here, I will just write. Uh, so see, the very basic way is this is my Vx, this is my 0, this is my V0. Okay, I will write nodal equation here. Okay, so 0 minus Vx by twice R, right? So this is 0 minus Vx by twice R plus 0 minus V0 by R is equal to 0, right? 0 minus Vx by twice R plus 0 minus V0 by R equal to 0. That's my nodal equation, right? So minus Vx by twice R, I will need some space over here. Okay, so minus Vx by twice R minus V0 by R is equal to 0. R and R get cancelled, right? So V0 is equal to minus Vx by 2. Correct, right?
Yeah, got it. Thank you.
So simply what you have to do, you just write down the nodal equation. And here, if you find this kind of question, you try to minimize the circuit as much possible and then apply the nodal equation, right? So life will be extremely simple. Okay. Any question on this? We will do some more complex ADC and DAC question in the next one. So I have taken time to explain you guys the Mealy and Moore machine, overlapping and non-overlapping sequence detector for both Mealy and Moore machine. And we have done couple of questions where we have discussed about the resolution. So see, what we have done is we have discussed about, okay, how much comparator will be required for flash type ADC. So everybody should go and understand flash type ADC and why this equation works, right? Then we have discussed about 8-bit DAC, right? And here what we have found out the equation for full scale output voltage. Then we have discussed about 8-bit SAR ADC. Okay, so the first one is the flash ADC, then the DAC, then SAR ADC. Okay, after that we have this R2R ladder. Okay, and then this is also a digital to analog converter, right? You are providing a digital value R2R DAC. Okay, and this is you are getting an analog value over here. We have discussed that, right? And then again one more question on R2R ladder, right? It's the same thing. You see, it's the same ladder. Okay, it's the same ladder. And Why the answer was that? You see 2R and 2R, okay, then R 2R, R 2R, right? So you have to see 2R and 2R, then R 2R, R 2R, right? That is the reason why it is called as R2R ladder, okay? So we have learned that, and then we have also seen one of the circuit again of R2R ladder, okay? You again see it is 2R, 2R, R 2R, R, then 2R, right? So again it's an R2R ladder. We have done one more questions on that. Okay, so everyone, you should understand the flash ADC, the SAR ADC, the DAC, all the DACs, R2R ladder and all, right? And how to calculate the full scale output, how to calculate the resolution, right? How to get the output voltages using the nodal equation. You should revise nodal equation if you have forgotten how to apply that. And you come back in the next session. We will do more complex questions on ADC and DAC. Okay, so that's all from my side for today. It was a long session. I hope you guys have understood what I have tried to discuss. If you have any question, feel free to ask right now. Okay, so thank you everyone for joining. Please make sure that you watch all the previous recordings, and you should also make sure that you practice as much question as you can to understand the concepts of the digital circuit, right? And if you face any difficulty, just come prepared with question in the next session. Okay, so thank you. Let's meet next Tuesday, same time from 6 to 7.
So as per the syllabus, this is the 8th week content, right? So, but we are seeing this in the 7th week.
For yeah, it as per the syllabus, it is 8 week, but because it is our seventh session, right? So that is the reason why I've written seven, session number 7. Okay,
Yeah, right.
so this is the seventh live session, so that is the reason.
Same thing happening in the assignment also. Assignment also, we are getting in the 7th assignment these questions. Obviously, I think it should be come in the 8th assignment, right?
Yeah, so this question which I have discussed, the Moore and Millie machine was for the seventh assignment. The ADC and DAC part is for the eighth assignment. Okay. So see, now
Actually,
you have at least 7 days to work on your assignment, right? And before your final assignment deadline, I will have one more session. Okay. So where we will do complex questions. So you will have at least 1 or 2 days before the final assignment deadline. Okay.
thank you.
Thank